So it's now my great pleasure to introduce our first plenary speaker for this conference, Professor Howard Wheater. Professor Howard Wheater is the Canada Excellence Research Chair in Water Security at the University of Saskatchewan, where he's been for almost the last decade. Prior to coming to Saskatchewan, he worked for 30 years in Imperial College in the United Kingdom. He's recipient of many awards in hydrology. The most recent prestigious award was the Jim Douge Medal from the International Association of Hydraulic Sciences. It's presented jointly from WMO and UNESCO. When Howard moved to the University of Saskatchewan, he was instrumental in setting up the Institute for Water Security, and he served as director for many years in that capacity. So Howard's main expertise is integrating hydrological studies with governance that advances water security, and I'm thrilled to, if you could join with me in welcoming Howard to giving the first plenary session.
Well, thank you very much for those warm words, and to you all for a warm welcome, and to George and the committee for inviting me here to such a great meeting. I'm really enjoying meeting people, and it's a very friendly atmosphere, and also an atmosphere in which people are coming together across disciplines and across sectors, where policymakers sit down and talk to scientists. And Bill actually sort of pinched my pitch really with his comments, because the title, Water Security in the Science Agenda, water security is one of the great challenges that we face as society in the 21st century. Governments are recognizing it, certainly big industry is recognizing it. There are huge challenges out there, and the question is, what do we as a science community do to help society manage these challenges? And I'm going to argue that we need to do all the things that Bill was saying, but also that Canada is providing some unique opportunities for global leadership in this area. So what you all know is that water is very multifaceted, and we tend to pigeonhole our water discussion in little boxes. We talk about the water, energy, food nexus, and so on. And of course, food is an important part of the water story, and vice versa. We use something like 18 to 90% of our consumptive water use for growing irrigated crops. And energy is a complex area where we get energy from hydropower, but equally thermal power stations need cooling. And the biggest user of electricity in the state of Arizona is pumping Colorado Water River. So certainly there's issues around the water, energy, food nexus that cross policy boundaries, but that's a simplification, because water provides water for industry, drinking water. It's a recipient of our wastes, and above all, it's a requirement to maintain healthy aquatic ecosystems. And so managing even the simplest reservoir system requires us to bring together land and atmosphere, land and water, water quantity and water quality, ecosystems in a holistic way. And as a community, we just haven't been great at grasping those challenges. There are lots of examples around the world why should we be concerned about this, and just a few from overseas. On the top line, the Aral Sea, a tenth of its previous size because of irrigation abstractions to grow cotton in the former Soviet Union. Thailand is an interesting story. You probably just about remember the Thai floods of 2011, but there was a $46 billion hit to global GDP, and a major hiccup in global supply chains of electronic components, particularly hard disk drives. So that's a message to us that water is really global, not only in the global water cycle, but also in the societal use of water and its products. Arsenic in Bangladesh, sometimes described as the world's largest mass poisoning. So under pressure of water resources, large-scale well development was undertaken without realizing natural contamination was a significant problem, and the health implications of that have been huge. To come a little bit closer to home, Canada and the US have had a recent history of major events. The California drought has just ended, but we heard a lot about that in terms of implications of overdraft of groundwater to try and keep North America's agricultural production going, and some very large statistics for impacts on energy production associated with that drought. The big recent story, Houston, very interesting story, $125 billion, current estimates of damage, hundreds of thousands of people evacuated, and one of these many instances of water being not just a natural system, but a human natural system. So why did Houston go underwater? Well, of course, there was an extreme event, but equally, there was no control on floodplain development. And so increasingly, as we live in a world which contains more people and more assets, we're placing these in areas at risk. And then coming a little bit closer to home, we don't have to go to the Great Lakes to worry about eutrophication issues. They're also a big deal in the west of Canada. Those are just some headline-grabbing stories, but I'm sure you're all aware of local examples of how these are playing out in your areas. The perception from outside that Canada, of course, is plentiful water resources, and that's true on an average basis, but water is a local issue, and we have all the problems I've just been talking about. So the West has always had a history of extreme events that have been damaging. So in the 1850s, the early European expeditions to the Prairies said it's really much too dry to think about settling there. And in fact, the paleo droughts in the Prairies were much more severe than the historical records. So drought is really still an existential threat for Western Canada. And then in recent years, we've had a whole history of flood events with large costs. So Calgary went underwater, Toronto had major floods. Actually, more or less since I arrived in Saskatoon in 2010, we've had floods pretty much every year for the last several years. We've got the tragedy of drinking water advisories across rural communities, particularly indigenous communities. We have massive issues associated with legacy wastes of all kinds, really billions and billions of problems. So in north of Saskatchewan, we have radioactive lakes. You're all aware of problems like Yellowknife sitting on 200,000 tons of arsenic. Many issues that will cost billions of dollars to clean up, and continuing operations which have their legacy consequences. So Canada has its full set of challenges, and then on top of that, we've got this incredible picture of rapid environmental change. So Canada is warming at one of the fastest rates in the world, and we're seeing that all around us, although I sometimes think we're a little bit like the frog in the saucepan, where the water's boiling around us and we're not really aware of what's going on. But you just have to look at the Rocky Mountains to see that the glaciers are on the way out, and particularly the last few years has seen rapid retreat. The winter minimum temperatures in the west and the north have increased by up to 7 degrees C in the last 50 years. The permafrost's thawing. Glacier retreat is having interesting implications. So in the Yukon, Slims River decided to change flow direction as the glaciers retreated. We've had our series of droughts, and then droughts are multifaceted. They affect certainly agriculture and the whole food supply chain, but they're also part of extreme weather, and we've had significant fire seasons in the north and the west over each of the last 5 years, with, of course, Fort McMurray being the outstanding story in terms of economic and human impacts. So we have increasing pressures globally and this challenge of rapid change. And so what do we do as scientists about that? And I think we need to organize, we need to come together, we need to break down barriers, and we need to be much more vocal in lobbying for significant developments that we need to help society manage the way forward. As we drive our systems increasingly towards their natural limits in terms of water resources, we need better science to understand that. And then, given this context of change, we, of course, need to understand what that means in terms of our ecosystems and our flows, terrestrial and aquatic ecosystems, and societal impacts. So, for sure, we need to do our individual science. But as soon as we start to talk about managing real problems in real places, then we see that we have to pull the science together across the disciplines. So we can't think about the Great Lakes without thinking about climate and climate change and extreme events and warming. We can't think about flows without thinking about water quality. And we can't think about water without thinking about ecosystems and their impacts and their feedbacks. And we can't think about water without thinking about the social controls and the social consequences of those controls. So we really have to bring together a range of disciplines from the natural sciences, the social sciences, economics, health sciences, in a much more productive way to address user needs. And there's long been some significant barriers to communication, and so we need to do a much better job at breaking down those barriers. We're very good at answering, as the science community, answering questions that we think people are asking and giving them solutions that we think they might be able to use, but there's very often been a real breakdown at that point. And I think we've now learnt from a very substantial literature of social science research that we need to engage all players in these problems at the early stage of problem formulation and bring all members of this stakeholder community along the ride as we pursue our research and develop the products that hopefully will help them to manage change. Canada's been providing some unique opportunities to move forward. I came to Canada in 2010 with a Canada Excellence Research Chair and a personal grant for $30 million, which was a career uniquely important opportunity and a rare event in most people's lives as researchers. So this gave me the first opportunity to build on the strengths that we had in the West and pull people together. We created a new institute, the Global Institute for Water Security. We started to use the local problems as a vehicle for bringing people together across disciplines. So I'll just talk a little bit about some of the issues and what we've been doing there, just to highlight what some funding and some interdisciplinary integration can achieve. For those of you that aren't familiar with the West, it is water limited. So as you know, all Canadians live in the South. The South Saskatchewan River is fully allocated in terms of water resources. 86% of the consumptive use is for irrigated agriculture. So very much along the lines of the global pressures. We're seeing huge changes. The dominant source of water is in the Rocky Mountains. So we're seeing the glaciers retreat, and they're an important source to support low flows in the rivers. We're seeing changing patterns of rain and snow, changing patterns of snowmelt, changing patterns of climate in the prairies, and a changing story of agricultural practices over very large areas. We have our issues of water quality, particularly nutrients, but also pesticides, and then equally concerns about emerging contaminants. We have a history, and a recent history, of very extreme events. And then these transboundary basins are complex. Provincial jurisdiction responsibilities, and the provinces have quite different approaches to water management. So Alberta, water is first in time, first in right. A different legal framework. And we even have contributions of flow to and from the United States. So actually, I think it's true that the Water Security Agency in Saskatchewan actually employs more lawyers than hydrologists. I live in the city of Saskatoon, and those of you who know it's a really beautiful city, and we live on the river. The important thing is that the flow in that river system, of course, it depends on what's going on in the mountains, but actually depends mostly on decisions made by people in Alberta, because they're entitled to take 50% of the natural flow. And it also depends on a very big reservoir, Lake Diefenbaker, the Gardner Dam, at the time the biggest earth dam in the world, which is regulated for hydropower, for water supply, for flood protection, for habitat maintenance, all these conflicting demands. So the water that we see flowing down is really a function of society's choices as to how much water is released. And one of the things that's been important for the system as a whole is the complete change in the natural flow regime. So this natural history of summer flows being driven by the snowmelt in the mountains, because of the large storage in the Gardner Dam and the importance of hydropower, that pattern is inverted. Downstream of Saskatchewan, of Saskatoon, the North and South Saskatchewan rivers combine into an important set of wetlands at Cumberland House, 10,000 square kilometres of freshwater wetlands, and those, of course, are very significantly impacted by the changing flows. And the communities that live there, Indigenous communities, Cree and Métis, depend for their livelihoods on the natural environment through not only hunting and fishing and trapping, but tourism associated with that. I've talked a little bit about droughts. The last big drought, multi-year drought, was the turn of the century, about a 6 billion hit to Canadian GDP. Flooding every year for the last several years, but probably most notable the Calgary floods, because we had extreme precipitation in the mountains. And funnily enough, we had some rain on snow, which created a large amount of runoff, but then the weather turned cooler and turned back to snow, so it could have been worse. But we had very severe events in the mountains, about 1 in 300 year return period. But when the flood got to Calgary, it was much more modest, something like a 1 in 30, maybe a 1 in 50 event. So why does a major city, the oil capital of Canada, go underwater from a 1 in 30 year event? Well, because we built in the floodplain, because the politicians have ignored the warnings, and people are there paying the consequences. So really we're faced consistently with this need for bridging the gap between science and policy, and for making results of our research meaningful to decision makers. A very interesting story about nutrients in the prairies. This is the tributaries of the South Saskatchewan River as they build. You can see the old man, the bow, the red deer. Left to right, they're feeding into the South Saskatchewan and Lake Diefenbaker. And on the left-hand side, we've got pristine waters in the Rocky Mountains. And you can see as we come through the heartlands of Alberta, the increasing phosphorus loads, particularly down the Red Deer. And interesting political story, because some years ago, Alberta adopted a guideline for total phosphorus, shown in red, 0.05 milligrams per litre, based on work that Environment and Climate Change Canada had been doing. And then they decided a couple of years ago, well, really, they had to throw it away because it was not helpful in terms of their management. They had no way of using that as a meaningful guideline. And as far as I'm aware, replacement guidelines are still not fully agreed for water at the upstream boundary between Alberta and Saskatchewan. So phosphorus is a big issue nationally and globally, but the politics of phosphorus management, as we all know, not least from the Great Lakes, are really complex and difficult and require very difficult answers to complex scientific problems. Lots of other things going on in the prairies. So agricultural management has had a massive impact through drainage. So contrast the natural landscape, which retains water on the landscape, good for flood protection, good for nutrient loading down, retention, and good for habitats. But the farmers achieve much more economic benefit from the landscape on the right, which gives them bigger land area to cultivate, improved access for large machinery, longer times on the ground to work. And so there are these big tensions playing out. And right now is a very interesting time in the prairies because Saskatchewan had legislation that notionally controlled drainage, but it was not implemented. And things have become so severe that they've now passed retrospective legislation last year that all historical drainage must be licensed. And that's a huge step and a very complicated step, and one that's playing out with significant political implications. I talked a little bit about the general background of warming that applies to the Saskatchewan River Basin, and we're seeing major declines in the mountain glaciers. They'll mostly be gone by the end of the century, and particularly the last few years have been really bad in terms of net mass balance decline. So there's some big questions about what replaces the glaciers, how do we maintain low flows, increasing focus on the role of groundwater in those mountain systems, and particularly frozen groundwater systems as we lose the glaciers. Really interesting things happening in the prairies. I've talked about drainage, which is part of the story, but we've seen real significant regime shift in terms of climate. Go back 20 years ago, all the flows in the prairies were spring snowmelt. And the last few years, we've seen summer floods that have been massive and widespread, never seen before. And you can see Smith Creek is an example where we've got this combination of climate change and agricultural drainage, and you can see the massive increase in runoff volumes that have been generated over the last recent years. And this is one of the reasons that's giving a lot of pressures behind this momentum for new legislation. So, what did we do with our $30 million? Well, we invested it in observing systems. So we put a lot of instrumentation in the Rocky Mountains. We maintained experimental systems in the boreal forest, which is such a huge landscape of importance for Canada. We have a lot of sites in the prairies. We started to work in various lake systems. So Lake Diefenbaker being one, but many others too. We started to build a series of models. We used innovative techniques for observing, so we've been doing a lot of work with drones, which have been giving us real insights into snow processes in the mountains and allowing us to improve our snow modeling, which is so important for floods and water resources. We're doing some interesting work at the moment with something that is going to revolutionize hydrology and water management globally, in my opinion, in the next few years. So many of you will be aware of the Swat Mission, which is going to be launched as a satellite mission in 2021. And this is going to measure water levels in our larger rivers and all our lakes globally. And in the meantime, then we're working on an airborne mission, including in Saskatchewan, on the South Saskatchewan, to understand the potential of this technique. So these new remote sensing ideas are going to be huge in terms of impacts for management and our science. One of the big issues for Canada, of course, is we don't know precipitation. Particularly, we don't know snow precipitation at all well. The areas are remarkably large. So there's some very interesting new science as we move our atmospheric models to the resolution where we can simulate precipitation processes directly and explicitly. And so we've been running 4-kilometer climate model and atmospheric model simulations over the whole of Western Canada. This is a huge enterprise in conjunction with NCAR in the US. And those have given us really important new insights into precipitation and forcing data for our hydrological models. we're able to build large-scale models of these river systems so we can think about managing them in a more integrated way. And to do that, we started to use remotely sensed data. And in particular, gravity data from space allows us to constrain the water balance in a way that we haven't been able to before. So much improved modeling performance, but also better identifiability of our models as we use these other sources of data. And this is the beginning of, I think, a very exciting new era of assimilation of remotely sensed data. As we look at our large river systems, we have to remember that they're managed systems, and this is a challenge. Until very recently, most hydrological models, and still many hydrological models, completely ignore the fact that we have dams, reservoirs, irrigation, and groundwater withdrawals. We are very short of information on these extractions and how they're managed. And so we've been doing a lot of work to include new algorithms in our large-scale models so we can simulate the unknown performance of these reservoir systems. And in the South Saskatchewan, we have dozens of reservoirs that are really important in terms of management. We put all that together, we're able to simulate flows across the region. Water quality, I talked a little bit about the nutrient problems. Buffalo Pound is a water resource fed by Lake Diefenbaker that then feeds Regina. And some of you may have picked up a couple of years ago, Regina lost a chunk of its water supply because of algal blooms in Buffalo Pound. So this is some work we've been doing with the utility there to understand the causes and the drivers and to provide real-time warning. And the graphs show the time series of increasing temperatures and increasing chlorophyll, and the bottom graph shows the relationship between the two. So I'm sure you're all aware that we're moving into a warmer world, and those increasing temperatures provide us with increased vulnerability to nutrient pollution. So we're seeing re-emergence of old problems in a warmer world. There's also so much to learn about the cold environments in our rivers and lakes. So we've been working on biogeochemistry of frozen lakes. And of course, what we need to recognize is the changing periods of river ice and lake ice, and answer the questions as to what that will do to the water quality of these systems. We've been developing models and having large experimental programs. Lake Diefenbaker is a couple of hundred kilometers long. It's a major resource. Carl Lindenspit's been developing some modeling of the different segments of that reservoir, different limbs, and then we have some dynamic simulation capability so we can look at both current climate and impacts of future climate in terms of lake processes, turnover, and so on and so forth. We've also been working to generate tools for users to look at water resource options. So a big issue in the Saskatchewan is that in an average year, we have underused resources, and so the irrigation community is really keen to expand irrigation. So this is a little slider-driven simulation tool that shows the flows in the South Saskatchewan River at the Alberta border, levels in Lake Diefenbaker, and the water that we need to pass to Manitoba. And then we can play some games. We can change the inflows due to changing climate and see what the impacts are on the system. And then we can talk to the farmers. We can expand irrigation and then see what the implications are in terms of economics and in terms of impacts on vulnerable ecosystems downstream. One of the big failures of the water community is to embrace the issue of climate change because we have been giving such difficult information to the users. So we say, well, precipitation may increase or it may decrease, and we're really quite uncertain. I mean, the models that we work with are very good on temperature, but they really are uncertain with precipitation. So we've been looking at new ways of trying to study system vulnerabilities. And this is a little example from the Alberta Southern Water Resource System. So if we look at the bottom axis, what happens if we change the timing of the annual hydrograph because we're getting warmer temperatures and earlier snow melt and earlier flows. And the vertical axis, what happens if we change the volume of runoff. And the color code shows the success of current operating policies, and then the blobs show where we can take scenarios from our climate models and see where they lie on this space. So this allows us to play what-if games and look at vulnerabilities and sensitivities and hence plan decisions around that, rather than saying, this is a scenario-based future and we're so uncertain that we really can't give you very useful guidelines. Underneath all this, there's a need to do a much better job at connecting with the social sciences. So we've been doing work with stakeholders to understand attitudes and values across the river basin, and they vary quite dramatically between provinces, interestingly. We've also been looking at storylines. So there are different storylines for the Saskatchewan Basin, depending on who you talk to. If you're an irrigator, there's fantastic potential from expanded irrigation. If you're a First Nation member living in the Delta, you've seen a progressive degradation of habitats, you have lost trapping, and you've lost hunting, and the fish are in decline. So you see quite a different story. So we've been working to understand the different stories coming from different perspectives, from industry, environment, Indigenous people, and agriculture. And we've been reaching out to people from various means for example, theatre performances. We put on a play called Downstream, which ran at various places across the basin. And we've also been working with First Nations with art exhibits, which have been travelling the deltas of the north. And working with communities and schools on educational projects, and also training people in terms of community-based monitoring. So with our little investment and a 7-year program, we've been able to do quite a reasonable job at starting to break down barriers, bringing people together, starting to produce meaningful tools, but just in one place. 2013 came along, and we had the opportunity to expand our scope with the Changing Cold Regions Network. So we now include the Mackenzie Basin, 1.8 million square kilometers, and we brought together 8 universities and 4 federal agencies to do the same kind of thing, try and understand the extent of change, try to analyze the historical changes that we've been seeing, which are quite complex and subtle and very interconnected, and then to do a better job at projecting into the future. So CCRN is just winding up. We have special issues in preparation at the moment. We had a spring conference in March to bring things together. We've been doing a lot of work. We've had to integrate the hydrological and the ecological community in closer ways so we can think about future land use change. We're seeing massive changes in the north, of course, shrub tundra greening, in the thawing permafrost regions, forests turning into wetlands, different connectivities, and changing patterns in the boreal forest and changing patterns of agriculture. So we've been working to project those changes forward, and then working with our climate models to run through scenarios of the future in terms of stream flows for the Saskatchewan and then for the Mackenzie Basin. The Mackenzie Basin, a very complex system, 20% water and lots of issues around permafrost and its implications. So those two enterprises, the 30 million investment in my chair led to the Institute, and then Changing Coal Regions was just a 5 million 5-year program, but it brought 25 million in-kind support and was really the next step in terms of integration of the community. And then we had a really unique opportunity because the Canadian government put money on the table for the universities to fight over, $1 billion. And the interesting thing was, in the second major part of the competition, each university could only bid for one area. So this led to some interesting politics. Waterloo, for example, I think decided to go from quantum computing, something like that. Saskatchewan went for water. And we were able to really integrate the Canadian community in a more complete way than had been possible. We put together a team of 4 universities, Saskatchewan, Waterloo, McMaster, Wilfrid Laurier, and each of those universities put their hands in the pockets to somewhere between $10 and $20 million. And so we were ultimately successful in winning a grant of nearly $80 million and a total program value, given the university support, of $143 million. So this is a milestone program. It aims to do a couple of things. One of the ambitions of the CFRF program is to help Canada develop a leadership role in international science, and we reckon we can be among the best in understanding coal regions' water and the way it's changing, bearing in mind that half the world gets its water resources from snow and ice. And then, of course, to address the needs of Canada. And I think this was a tough competition. So we were up against quantum computing, we're up against the health sciences, but the agenda for water is now, I think, sufficiently compelling that we were successful and were able to pull together this major program. So we have 18 universities across Canada represented. We have a whole range of federal agencies involved, and we have a couple of hundred stakeholder communities, ranging from indigenous communities through to particular industrial sectors, through to government, such as Environment and Climate Change Canada, Parks Canada, Natural Resources Canada, and so on. So it's a very exciting program. We just had our first annual meeting where all the participants came together last month. So far, we're funding about 500 researchers. The program is important in the way it's constructed. We have a pillar which is about science, and that includes health sciences, social sciences, atmospheric sciences, ecology, hydrology, about diagnosing and predicting change. We have a big emphasis on big data and decision support systems. There are massive opportunities from remote sensing and social media for improving our access to data, the use of data in modeling, and the use of data to communicate with people and to warn. And that's a big part of the program. But the biggest part of the program, where most of the money is being spent, is designing user solutions. So working with users to formulate problems to meet their requirements, and then involving them to produce solutions that they can use. So here's our little schematic. On the bottom right, this is Canada as a world-class observatory. So it's full of new sensors and drones. We're doing a lot of really interesting work with sensor development and remote sensing. We're engaging the computer science community so we can do a better job at building models, assimilating data, developing apps, and so on. And then we have a huge component focused on user engagement and information sharing. And we're actually employing a whole set of specialists to help us in knowledge mobilization and user engagement. The main themes: we want to improve disaster warning, and Canada has a huge need for this. There is no national forecasting capability in Canada, probably the only developed economy that doesn't have that. The responsibilities lie with the provinces. We need to do a better job at predicting water futures, and we can focus our science to do that. And then the third area of delivery is really informing users so that they can adapt to change and manage the risks that we see upcoming. So I just wanted to mention a few of the projects that are being funded, because some of them will involve some of you, and some of them may resonate in terms of outputs being useful. So we have a climate precipitation extremes, which is multi-institutional but led by Ron Stewart and Francis Spheres. We have a project focusing on the northern water features, particularly Northwest Territories, led out of Laurier. John Giese, together with Mark Servas at Waterloo, have got quite a cool project using new instrumentation, so very high resolution mass spectrometry and new eDNA state-of-the-art tools to explore what we can do in terms of looking at ecosystem health and resilience and tracing contaminants. And I think that there's some massively exciting opportunities as we open those boxes of those new tools. Helen is leading a project on blooms. Marion McRae from Waterloo is leading a pan-Canadian project on agriculture, thinking about agricultural futures and nutrient management issues. Mike Waddington looking at the boreal forests, including fire as a major component. There's a prairie project being led out of Saskatchewan, and an integrated modeling program which aims to look at water quantity and water quality and hydroeconomics in an integrated system. A mountain project led by Sean Carey, a lake project which is initially focusing on the Laurentian Great Lakes, led out of Waterloo, Nandita Basu with Philippe van Kapellen, but ultimately their ambition is to go pan-Canadian. And then Claude Duguay is leading a remote sensing and new sensor project. So those are some of the bigger projects. They're funded initially for 3 years with a potential expansion to 7-year programs. But I think they will have resonance to some of you here. We had issues with Indigenous communities, so we put out a call for proposals, and they didn't like that because it was really inconsistent with their traditions and values. So we've had an ongoing dialogue over the last year or so, and in fact, our first annual meeting about a month ago was held jointly with the Six Nations just off the Master Campus. So they are now engaged, and we have some programs moving forward closely with them targeted to meet some of their needs. So where is this program today? Well, we're about, it was, the flag dropped in 2016, but it's taken us a while to get organized. So far, we've funded 33 projects across 15 universities, 150 faculty, nearly 500 researchers for the first 3 years, and 210 partner institutions. We spent 23 million on grants and another 15 million on core teams. But those grants have already leveraged another 26 million in cash support and 120 million in kind support. So we've got 185 million for the first 3 years of the program. We're big enough to attract national interest, and so there have been some spin-offs. For example, Environment and Climate Change Canada is investing $90 million in improved hydrometric and forecasting services. And then it's also attracting quite a lot of global interest. So we're playing roles in UNESCO programs to do with alpine environments. We're a regional project for the World Climate Research Program, and then we're heavily involved in Future Earth Sustainable Water Project. It's exciting times. We think the world's largest university-led research program ever, anywhere. I'm proud that we've been able to achieve that. I'm impressed that Canada has been able to resource this and that the community has come together really in a unique way. So all of those major projects all involve multiple investigators from multiple disciplines across multiple institutions. And we're really building bridges that will, I think, provide lifelong continuity of effort. So we have big challenges, but we certainly have a huge opportunity here, and the challenge now is to fulfill on those ambitions. So just to wrap up, as your president mentioned earlier, really water security is a very big issue for society, and for us as scientists, but it provides us with unique opportunities. And we're facing a future with some tremendous potential for scientific development and improved understanding and modeling tools. We absolutely need to understand these systems better as they change and their vulnerabilities change. And as I've argued, and others have argued before me this morning, we do need to bring people together across disciplines and with users, and we need to do a much better job of connecting science and society. And that's hard work. It's hard work to learn to talk across disciplines, and it's hard work to work on those relationships that we need to foster with the user communities. We do need research to deliver this, and Canada has been providing that and providing global leadership in that area. So it's an important time. Now's the time to move forward. Now's the time to come together. Canada is at the forefront of rapid change. We have the opportunity to provide leadership. I think I'll conclude there. Thank you very much.